Hey everyone, welcome back. I know in case you missed our class last time or if you recently joined because of the schedule change, I'm going to go over what we did on the second day of class. Um, so we're going to cover two things. We're going to cover evaluating expressions as well as the real number system. You should have a notebook for the class to take notes in. Um, so as you can see, I've already taken the notes that we were taking today and put them in my notebook. Um, I suggest actually writing them down. There was a question on whether you can do your notes in Word, and the only thing I see with that is that if you're taking those as we do them in class, it's hard to go ahead and do them pretty fast in Word when you're putting the equations in. It doesn't really, it takes too much time to do that. You lose what we're focusing on at the moment. So do make sure you are taking notes, and you can pause the video at any time if you need more time to go ahead and copy them down. Without further ado, let's go ahead and get started. So we're going to go ahead and start here. We're going to start with evaluating expressions. We're going to watch a short video. You can find this on Khan Academy. It's just a great review for just evaluating expressions, a review for what we should know already. But I do know it's been a while since a lot of us were in the classroom. So just a quick review.
A local hospital is holding a raffle as a fundraiser. The individual cost of participating in the raffle is given by the following expression: 5t plus 3, or 5 times t plus 3, where t represents the number of tickets someone purchases. Evaluate the expression when t is equal to 1, t is equal to 8, and t is equal to 10. So let's first take the situation where t is equal to 1. Then this expression right over here becomes, and I'll use that same color, it becomes 5 times 1, 5 times 1 plus 3. 5 times 1 plus 3. And we know from order of operations, you do the multiplication before you do the addition. So this will be 5 times 1 is 5 plus 3. And then this is clearly equal to, this is equal to 8. Now let's do it when t is equal to 8. So when t is equal to 8, this expression becomes, and I'll do the same colors again, 5 times 8, 5 times 8 plus 3, plus 3, same color of green, plus 3. And once again, 5 times 8 is 40. 40, and then we have the plus 3 there, so this is equal to 43. And so we have the last situation with t is equal to 10. I'll do that in blue. I'll do that in blue. So we have 5 times 10. So 5t is 5 times 10. Instead of a t, we put a 10 there. 5 times 10 plus 3. Plus 3. That's a slightly different shade of green, but I think you get the idea. 5 times 10 is 50. We do 50, and then we're going to have to add 3 to that. And that is equal to 53. And we're done.
All right, so that's just a quick review. And in the video, you did hear him talk about order of operations. Sometimes we call this PIMDOS. So we have step one, which is the P in PIMDOS parentheses. This is evaluate all expressions inside grouping symbols. Then you're going to evaluate powers, or also known as exponents, so the E in PIMDOS. And then we have multiply and or divide from left to right. So what that's saying is that when you read, as we read left to right, you do whatever you see first. If you see a division, you do that first. If you see a multiplication, you do that first as you read to left to right. And then after that's all said and done, we go ahead and add or subtract from left to right in the order that we see it. Now's a good time to go ahead and pause the video if you need time to go ahead and copy down those steps. Right, so now we have an example of evaluate x minus y cubed plus 3 if x equals 1 and y equals 4. So we're going to go ahead and substitute in 1 for x and 4 for y. And we're going to follow our order of operations. So we're going to go ahead and take care of what's inside that parentheses 1 minus 4 to get negative 3. And whenever we're working with exponents, it's always a good idea to go ahead and put what we're raising the power what we're raising the power of inside a set of parentheses, especially if it is a negative number, just to make sure that when we raise the power, and whether it's you're doing the calculation yourself or if a computer or a calculator is doing the calculation for you on raising the power, that you make sure the negative is applied correctly. So we're going to go ahead and take negative 3 cubed, which is negative 27, and then we're going to add 3 to it to get negative 24. So if you need to take a moment so you can have time to copy this down, go ahead and pause the video. We're also going to take a look at looking at typing this into the calculator online that we could use. So here we have Desmos.com. It's a great online calculator tool to use at home. So under here, they have several types of calculators. We're going to look at the scientific calculator. And so you can either type this in, you can also do this on your phone. They have a great app for that, or you can go ahead and do it on your computer. If you're going to do it on the computer, you can either type using your keyboard or use the keypad they provide for you. So we're just going to go ahead and do parentheses 1 minus 4, close parentheses. To raise that power to 3, we're going to do a to the b, put a 3 in, and then plus 3. So if you needed some help figuring out the calculation, this is a great place to go. And you see that we still get negative 24. And going back to our lovely PowerPoint that we have here, we're going to go ahead and go to a UTry. I go ahead and pause this now and go ahead and try this on your own. I'm going to wait about 5 seconds and then we'll go ahead and continue. But do take a moment to pause and go ahead and try this one. This is a UTry. In class, you would do this on your own and then we'd come back together. All right, so we're going to go ahead and work on this one here. So if we were to do this, we need to remember that we have 5 here for G, for F and 2 for G. So we're going to plug this in and we should get 3. So I'm just going to, everywhere I see a F, I'm going to substitute in 5. I'm going to go ahead and stick that inside some parentheses. Keep my symbols that we have. And then in parentheses, I'm going to put a 2. Close parentheses, put my exponent of 2, and then minus 3, and in parentheses, go ahead and put a 2. All right, so there's nothing to do here with this 5, so we're just going to bring this 5 down. So I'm going to do 2 squared, which is 4, and 3 times 2 is 6. And then we're just going to add as we see left to right, and we get 5 plus 4, which is 9, minus 6. And when we simplify that, we do get 3. I am doing this on my computer with the trackpad, so please excuse me for it not quite being straight and just being a little messy. It is being done on the trackpad of my computer. So let's go to our next example. Evaluating expressions, something you would actually probably be most likely used for is filling out a formula and telling me what you get. This would be in your math class, science class, or if you're just trying to find out something for yourself in maybe, the area of something, you would use a formula and just evaluate. So we have the formula for the area of a trapezoid is A equals 1/2 h times the sum of the bases, where h is the height and b1, b2 represents the measurements of the bases. So we're going to find the area of a trapezoid with base lengths 13 meters and 25 meters and a height of 8 meters. So we're going to take our formula and we're going to substitute in 8 for h, 13 for one of the bases, and 25 for the other base. And using our PIMDAS, we're going to go ahead and evaluate what's inside our parentheses. So 13 plus 25 is 38. We're then going to multiply as we go left to right. So 1/2 times 8 is 4, and 4 times 8 is 152. And so since we are actually using this to find an area, we need to make sure that we go ahead and say it's 152 squared meters. You might also see this written as 152 meters squared is the other way you might see it written as. But do remember that to include your units, that is very important, especially when we're looking at area, lengths, or volumes. It just can make sure that we know what we're actually talking about. So for lengths and just in general, you're just going to use whatever the measurement is, so it would just be plain meters. If you're doing area, it's going to be your units squared, so meters squared. If you're doing volume, it's going to be units cubed. So you're going to try to pretty much keep it track with the dimension of the object that you are looking at. All right, so here we have a formula for the volume V of a pyramid. V equals 1/3 base times height, where B represents the area of the base and H is the height of the pyramid. What is the volume of the pyramid shown? So go ahead and take a moment, pause the video, and go ahead and try it on your own before we go over this. All right, so here we have, they give us our formula, which is really nice of them. And they also remind us that the B represents the area of the base, meaning it's not just one of these lengths. I need to go ahead and use both of them. Since my base is a square or a rectangle, we know our area is equal to length times width. And in squares, we usually just say the side length squared, but we're going to go ahead and remind ourselves that area of a rectangle is length times width. So we're going to go ahead and we keep our 1/3. And to get my area, I'm going to multiply my two side lengths. So we're going to do 5 times 5. And that is my B value. And then we're going to multiply by the height of 6. So we're going to simplify what's inside the parentheses first. And we get 5 times 5, which is 25. And we're going to multiply that also by 6. In this case, I'm going to go ahead and multiply 25 and 6 to help myself out here, since we are doing multiplication. And that gets me 150. And so when we're multiplying a fraction and a whole number, especially if the numerator is 1 in the fraction, that's going to be the same thing as if I just divide by the denominator. So 150 divided by 3 is 50. And because we're talking about volume, we're going to go ahead and use cubic centimeters for our units. So our answer here is C. If you do have some issues with multiplying with the fraction, you should always definitely, when needed, go ahead and get that online calculator to look at. So in Desmos, we could go ahead and do this. So I would do 1 divided by 3, and notice it turns it into a fraction. Do make sure you get out of the numerator before you continue. And I can go ahead and do 25 times 6, since 25 represents my B value, and you see we do get 50. All right, so that concludes our review over evaluating expressions. Next, we're going to go over the real number system. And then we're going over the real number system because we actually do have imaginary numbers. We'll be going over that later on in the year. But the real number system is just a way to classify numbers into sets and subsets. So here's the real number sets system that we have. So if you kind of think of it, everything we're going to talk about today is in the real number system. No matter what, everything's a real number at the moment for us. So, and we can break up numbers into two big groups. We can either be rational or we can be irrational. So these are the two major subgroups. If you're real, you're one of these. You're either rational or irrational. And rational is basically is a number that can be written as a ratio of two other numbers. So that's why if you look at it, if you cut the word rational at the O, it actually has the word ratio in there. It's just a ratio of two numbers, so a fraction. Whereas irrational means I cannot write it as a fraction. There's no way it's going to happen. And so a couple of examples of that are like pi. It's a never-ending decimal. It just keeps going on forever and ever. When we take the square root or a root of a non-perfect power, so the square root of 3 would be a never-ending decimal. The square root of 5 would be a never-ending decimal. And from there, once you decide on if it is between those two, we can go ahead and classify even more if it is a rational number. So if you look at the square, we're cut in half here, or a little more in 2/3 to a third. We're cut here that we have, within rationals, we have more subsets. And we're actually going to work our way out of the subsets. So we're going to start with the most restricted subset, which is the natural numbers. Natural numbers are also known as counting numbers. And so they would start at 1 and continue on 2, 3, 4, 5, 6, using the numbers you count by. So they're called the natural number system, or also you might hear them called as counting numbers. From there, we get a little bit more, we add a little bit more. We can add in this, we have whole numbers, and whole numbers is all the natural numbers, but we're gonna add one more number of 0. So all the positive numbers with 0 added in it. So another way to think of it would be they're non-negative. Next we have integers. So integers are made up of all the naturals, all the whole numbers, and then we're gonna go ahead and add a little bit more and say we're gonna also include all the negative versions of the whole numbers. So positive and negative version of whole numbers is what's included in our integers. Now, if you're not a whole number or a positive or negative whole number, then, so for example, that would be like 0.25. You are real and rational, but you're not going to reach any other subset. Versus if you are the number 2, you're going to qualify for all the other subsets under rational. If you are -2, you're only going to qualify to be in the integers. So do take a time to go ahead and copy this down. It will be a very good reference to have. And yes, you really should also copy down the examples that are here. That way you do have something you can reference. And what they mean, by the way, if you look at here, we have where they say the word letter. These are shorthand when we talk about number sets. So the shorthand for real numbers is the R. Sometimes you might see it in bold and R. You might have seen a math teacher in the past say, oh, we're going to say this is all real numbers, or negative infinity to infinity is what you might see, that you would have seen this double bolded R. Then you have Q, which stands for rationals, I for irrational, Z for integers, W for wholes, N for naturals. I do not know why they pick Z and Q for their rationals and integers. I can see why they didn't pick R, because R was already being used by real numbers. So I'm not quite sure. And integers might just because it was already being used by, I was already being used by irrational. But do take a moment, pause it, and go ahead and copy that down so that you do have it in your notes. We are going to watch a short video over classifying numbers. This is just a really good explanation of just practicing and putting them in and how they're really like nesting dolls once you're on the rational side. But he does a very good job of going over several examples.
So we have a bunch of numbers listed up here, and my goal in this video is to see if we can classify them into different types of number categories. And let me draw the categories. So this circle over here, this represents all of the numbers that can be represented as the fraction of two integers, and of course the denominator can't be equal to 0 because we don't know what it means to put a 0 in the denominator. So let's call these, or the standard way of calling these things that can be represented as a fraction of two integers, we call these rational numbers. Rational numbers. And if something cannot be represented as a fraction of two integers, we call irrational numbers. Irrational numbers. Irrational numbers. And the size of these circles don't show how large these sets are. There's actually an infinite number of rational and an infinite number of irrational numbers. So these are the irrational numbers. Irrational. So these cannot be represented as a fraction of two integers. And then within rational numbers, you have integers themselves. So I'll do that let me do that in this blue color. Integers. So integers are numbers that don't have to be represented as a fraction or a decimal. So these are integers right over here. Integers. And then a subset of integers are whole numbers. So if you essentially say the non-negative integers, you're then talking about whole numbers. So let me do that subset right over here. So these are going to be the whole numbers. So whole numbers. Whole numbers right over here. And actually, let me just label it all. These are rational. Let me do it in that same color. Rational numbers. And of course, irrational numbers. Irrational numbers. Irrational numbers. And an integer, well, if I could say literally, that is an integer. Let's think about the integers. But I wouldn't say let's just think about the rational. I would say let's think about the rational numbers. All right, now that we have these categories in place, let's categorize them. And like always, pause the video. See if you can figure out what category these numbers fall into. Where would you put them on this diagram? So let's start off with 3. This is positive 3. It can be definitely represented as a fraction. You could represent it as 3 over 1. But it doesn't have to be represented as a fraction. It literally could be just a 3 right over there. But it's also non-negative. So 3 is a whole number. So 3, and maybe I'll do it in the color of the category. So 3 is a whole number. So it's a member of that set. But if you're a whole number, you're also an integer, and you're also a rational number. So 3 is a whole number, it's an integer, and it's a rational number. Now let's think about negative 5. Now negative 5, once again, it can be represented as a fraction, but it doesn't have to be. But it is negative, so it's not going to be a whole number. So negative 5 is going to sit right over here. It's an integer, and if you're an integer, you're definitely going to be a rational number, but it's not a whole number because it is negative. Now we have 0.25. Well, this for sure can be represented as a fraction. This is 25 hundredths right over here. So we can represent that as a fraction of two integers, I should say. It's 25 hundredths. But there's no way to represent this except using a fraction of two integers. So 0.25 is a rational number, but it's not an integer and not a whole number. Now what about 22 over 7? Well, here it's clearly represented already as a fraction of two integers, but I don't think I can represent this any other except as a fraction of two integers. I can't somehow make this without using a fraction or some type of decimal that might repeat. So this right over here, this would also be a rational number, but it's not an integer, not a whole number. Now this over here, 0.2713, and then the 13 repeats. This is the same thing, 0.27131313. That's what that line up there represents. Now, you might not realize it yet, But any number that repeats eventually, and this one does repeat eventually, you have the 0.13, or you have the 0.27131313, any number like this can be represented as a fraction. For example, and I'm not going to do it here just for the sake of time, but for example, 0.3 repeating, that's the same thing as 1/3. And later on, we're going to see techniques of how do you convert this to a fraction of two integers. But for our sake, we just know that this can be represented as a fraction of two integers, just the way that 0.3 repeating can be. And so we would put this under rational numbers, 0.2713 repeating. But you have to represent it as either as a decimal or a fraction of integers. If you didn't have to, then it could have been an integer. But we'll throw it up there in rational numbers. Now the square root of 10. Square root of 10. This is interesting. So any square root of a non-perfect square is going to be irrational. So this is going to be irrational. I'm not proving it to you here, but you cannot represent this as the ratio of two integers or a fraction with two integers, with an integer in the numerator and an integer in the denominator. This will be, if you were to represent it as a decimal, it will not repeat. It'll just keep being new digits. It will not repeat over time. So this right over here is an irrational number. It's not rational. It cannot be represented as the ratio of two integers. All right, 14/7. This is the ratio of two integers, so this for sure is rational. But if you think about it, 14/7, that's another way of saying 14/7 is the same thing as 2. These two things are equivalent. So 14/7 is the same thing as 2. So this is actually a whole number. It doesn't look like a whole number, but remember, a whole number is a non-negative number that doesn't need to be represented as the ratio of two integers. And this one, even though we did represent it as the ratio of two integers, it doesn't need to be represented as the ratio of two integers. You could represent this as just 2. So that's going to be a whole number. 14/7, which is the same thing as 2, that is a whole number. Now 2 pi. Now pi is an irrational number. So if we just take a multiple of pi, if we just take an integer multiple of pi like that, this is also going to be an irrational number. If you looked at its decimal representation, it will never repeat. So that's 2 pi right over there. Now what about, let me do that same, since I've been relatively consistent with the colors. So this is 2 pi right over there. Now what about the negative square root of 25? Well, 25 is a perfect square. Square root of that's just going to be 5. So this thing is going to be equivalent to -5. So this is just another representation of this right over here. So it is an integer. It's not a whole number because it's negative, but it's an integer. Negative square root of 25. These two things are actually the same number, just different ways of representing them. And then you have, let's see, you have the square root of 9 over 7. Well, what's the principal root of 9? This thing is going to be the same thing. This thing is the same. Let me do this in a different color. This is the same thing as square root of 9 is 3. This is the principal root of 9, so it's 3/7. So this is a ratio of two integers. This is a rational number. Square root of 9 over 7 is the same thing as 3/7. Now let me just give you one more just for the road. What about pi over pi? What is that going to be? Well, pi divided by pi is going to be equal to 1. So this is actually a whole number. So I could write pi over pi right over there. That's just a very fancy way of saying 1.
And so he went over several examples of how to go ahead and classify numbers. We're going to go ahead and practice this. So I have included the chart just for reference. So looking here, we're going to name all the sets which the square root of 6 belongs to. So we're going to look here, and I'm going to ask, is there any way I could simplify this? And well, the answer is no, because 6 is not a perfect square. So that means it's not going to be any simpler than that. This is the nicest way I can write it, which tells me it's going to fall in like we have here with the square root of 3. So it's going to fall under that example. So this is going to fall into real and irrational. All right, our next example is we're going to take a look at 5. And so I can already tell you it's going to fall under rational. And it's also going to be an integer because it is a whole number. And since I use it when I'm counting, it is also natural. So it falls into 5 categories. It falls into a real number, a rational, an integer, a whole, and the naturals. Our last example to take a look at is going to be negative 2/3. If you take a look, what we have right here is we do have positive 2/3 here. And since it is a fraction, I know it falls into rational. So it's real and rational. And then I'm going to see, does it fall into an integer? My answer is going to be no, because this is a decimal and it's not going to be able to change into a whole number. So it is only rational and real. All right, so go ahead and take a moment to pause and see if you can classify the number 3/5 into which sets it could belong to. Is 3/5 irrational and real? Or is it rational and real? Or is it natural, whole, integer, rationals, and real? Or is it none of the above? So go ahead and take a moment, pause, and then try it on your own. All right, so here we have, it's going to be natural and real since it is a fraction. That is the very definition for our ratio here. So that's what we have here. And because it's not a whole number, it's not going to get clarified any further or classified any further. All right, here is another U-try. Go ahead and pause it and go ahead and see if you can classify negative 2.52 repeating into which number sets: irrational and real, rational and real, or natural, whole, integer, rational, and real. All right, so here we have a repeating decimal. So the important thing to remember is that it is repeating. And if you remember in the video, he did go over an example of a repeating decimal. And then eventually everything that has a repeating decimal will be able to go ahead and be written as a fraction. One good example we have of a repeating decimal, sorry about that. One thing we have of a repeating decimal that we can remember is if you think of the number 1/3. Now, in general, most of us remember that this is 0.333, and if you notice, it's just going to keep going on and on. So we would just say it's a repeating decimal. That's what it is here. And so as you can see, this does go ahead and repeat, but I can also write it as a fraction, so that should remind you that any repeating decimal is a rational number because it can be written as a fraction. In our last example, or last U-try, we have this define square root of 5 to which sets. Is it A, irrational and real? Is it B, rational and real? C, natural, whole, integer, rational, and real, or none of the above? So go ahead and take a moment to pause the video and go ahead and try this one on your own. All right, so we're going to take a look here at square root of 5. And I'm going to say, I know 5 is not a perfect square, so it's not going to simplify any further. Since I know that, it is going to be irrational. All right, and so that concludes our notes. Do make sure you do your assignment that is online in ALEKS. It's called the Lesson 1-1, 1-2 assignment. And that's all we have for today, and I hope to see you in class next time. All right, bye.